Hi everyone, welcome back to the channel. In today's video we're going to be looking at an example of an application of differentiation, which is rates of change. Well, another name that it's been called is related rates, okay, in case you have a book that uses a different title. So let's get to it. So we have an example here, word problem. Word problems are always tricky. The radius of a cylinder increases at the rate of 0.2 centimeters per second, while the height decreases at the rate of 0.5 centimeters per second. We have to find the rate at which the volume changes at the instant where your radius of the cylinder is 8 centimeters and the height of the cylinder is 12 centimeters. Now, whenever you do word problems, it's always a good idea to do a diagram, if you can, right? So what we've got here is we have a cylinder, they say, cylinder that looks probably something like this, right? Like that. We have, let me do it like this, we've got a height. We have a height. That would be our h, and we have the radius of the cylinder, right? And the radius is going to be from the center to the edge, right? So that is going to be r, right? So it says your cylinder increases at the rate of, the radius increases at the rate of 0.2. So this bottom bit is increasing while your height is busy decreasing. Now, if you think about it, if you had this shape in a piece of clay, right, and you pushed your hand down on the top of that piece of clay, you can imagine the radius of that piece of clay becoming fatter and the height of that clay becoming shorter. Right? You want to know what is the rate of change of the volume at the instant where the radius is 8 and your height is 12. So because we're working with volume, you must always work from what you know to what you don't know. Okay? So we know that the volume of a cylinder of this shape, right, is basically the cross-sectional area times your height. Your cross-sectional area is a circle, which means you are looking at pi r squared times your height. Times your height, right? And this is what you are going to be working with. Because remember, what are you looking for? You are looking for the rate of change of your volume. So whenever you see rate of change or rate at which something changes, it means you're looking at a derivative, yeah? And you are looking at the rate of change over time, which means you want volume, the rate of change of volume with respect to time, okay? Which means that time in this case is your independent variable. It doesn't depend on anything. You know, they always say time marches on and waits for no man. It means it's completely independent, which means volume here is your dependent variable. But your volume is also dependent on what r is and what h is, okay? So there's a lot of theoretical ways that you can set this up. I'm going to present it the way I understand it, and you can use it or not. You must use whatever works for you. So from these two, I know that you can see from your equation here, volume is dependent on two different variables. You have r and you have h, right? And remember, they said in the question that your radius is changing at, what was it, 0.2 centimeters per second, and your height is changing at 0.5 centimeters per second, which means that your radius is dependent on time, right? Which means your radius here is dependent on time, and your height is also dependent on time, okay? But what you want to get dv dt, okay? So remember, I said this one here is the dependent variable, dependent. That over there is your independent, right? And these ones we are going to call our intermediate variables, right? But you want v with respect to t. It means that you need to go through r and h effectively, right? And this is where we come with partial derivatives, because your v is dependent on r and h, but your r and your h are only dependent on t. Okay? And if you want to find the expression for dv dt, you have to use every single piece of this diagram. You must include all of the variables. So we're going to start off with r and v, right? So it's basically chain rule. So it means that we've got dv dr, right? And partial because it is partially dependent on r. If you cover up this bottom piece, don't look at the bottom piece, only look at this little piece here, right? V is dependent on both r and h, right? So it has to be partially dependent on r. Times the derivative of r with respect to t, because r only has one independent variable. Okay, so this deals with the one leg. Then you have to deal with the other leg. So the first part is v is partially dependent on h. Oops, let's make that black. V is partially dependent on h. H is completely dependent on t. Right? And this is what we're going to be using. Okay? Because if you didn't have the intermediate variable here, you would just have v is dependent on t, which is why this here is just an ordinary derivative. Okay? So now, let's see. We need to work out now what these expressions are. Because you know what the r dt is, right? That is just the rate of change of r with respect to time, and that's going to be the 0.2. So you know what this is, because that is just equal to 0.2. You know what this piece is, because that's the change of h, or the change of your height with respect to time, and that is going to be 0.5. What you don't know are these two expressions here. Yeah, so you're not going to be able to work out dv dt if you don't have that. But you do know what v is. Right? You've got an expression for v, and we said earlier it is pi r squared h. So you can then find what dv dr is, and you can find what dv dh is. Okay? So dv dr is where you assume that h is constant. Yeah? Which means you're going to have, and you are differentiating with respect to r. So it's just going to be 2 pi r times h. The partial derivative of v with respect to h is where your r is assumed to be constant. So then that is just going to be pi r squared. Okay, so now you've got expressions for dv dr, or the partial derivative dv dr, and the partial derivative dv dh, and you can substitute it into your equation over here. Okay, so let's do that. So we substitute the partial derivative dv dr, so that's going to be 2 pi r h. We know that dr dt is 0,2. Partial derivative of dv dh is going to be pi r squared, and the rate of change of h with respect to time is 0.5. So there you can see you have an expression now for dv dt. And if you go back to the question, if we now go back to the question, it asks you, what is the rate at which the volume changes at the instant where your radius is 8 and h is 12. So now you can substitute these two values into the equation you've got, right? And we just replace all of these. You know that pi is just a constant to be 8, and h is 12 times 0.2 pi, and that's going to be 8 squared, 0.5. And when you calculate this, you're going to get a value of 20,1 centimeter cube per second. Right? This means, what does this answer mean? It means that your volume is increasing by 20,1111 cubic centimeters per second, right? How do you know it's increasing? Because of the positive sign here. Okay, so you can write that. You can say, therefore, the volume, and this is obviously at that instant where your R is 8 and H is 12, is increasing. It's increasing at a rate 20,11 cubic centimeters per second. Okay, and there you have it. So just to summarize, whenever you are working with a word problem, always try to sketch the problem and then see what do you know about that sketch. Write down everything that you know and that you can deduce from the word problem, and see what you can use in order to set up your formula for what you want to find. So in this case, you wanted to find the rate of change of volume. So you set up an equation for that dV dt. And then you just substitute in your values and you get a result. I hope this video was helpful to you. Please give me any kind of comments below. Is there something you'd like me to do? Maybe there's another example you'd like for me to go through, another rate of change or related rates problem. Please let me know. And I will see you next time. Bye.